just a quick overview of the agenda. We'll have an introduction of ABC21, and then Professor Guilherme will introduce the topic of the weather files. And at the end, we'll have an open discussion with questions and answers and a closure. If there are any questions you send to us, if not, I'll give the floor to Lorenzo to start introducing a little bit about the project. Please, Lorenzo.
Yes, thanks. So thanks for the introduction. So the project is a collaboration between Europe and Africa, scientific coordination by Pagliano and Erba, and the administrative coordination by E7, as you have seen. The idea is, and the objective is to revive and update knowledge about the bioclimatic architecture and local bio and geosourced materials, learning from each other, learning especially from the experience of the new wave of African architects. And one of the new conditions for which we have to do this update of what is known about passive buildings is the quick evolution, unfortunately, of weather, of general climate and local weather. So we must design new buildings and cities and renovations to fit with these new warmer conditions and the extreme events that are more frequent. From this, the need for quality checked future weather files as input for the simulations that in our view should be provided by or certified by a public initiative. And you find a report on future weather files, which is the subject of the presentation of Professor Guilherme today, examples of those files on the website. The project does a number of other things, including promoting a common language to make possible and precise this exchange between experiences based on the most recent international standards, ISO 52000, for example, and focusing, obviously, talking of passive technologies on the indicator, which is a description of the performance of the envelope, of the building envelope. For example, energy need for cooling is the heat to be extracted from a conditioned space to maintain a certain temperature during a given period of time. And this is depending on the features of the solar protections, of the thermal insulation, and so on. So it's physically defined objectively and without the uncertainties and policy complications of discussing primary energy, which is one relevant parameter. And there are already a number of, we're also exploring the regulations. There is a part of the project which deals with policy advancements. And for example, Morocco has a building code which limits the value of energy needs for heating and cooling. So it's strictly focused on the envelope. Switzerland, to talk about Europe in general, has a mandatory limit for the value of energy needs for heating and mandatory installation of external solar protections, minimum thermal mass before installing air conditioning, if still needed. There is also a discussion that you will find in the deliverables about the indicator net zero energy, which is very briefly a difference between exported renewables to the grid minus imported primary over a year. You can get a balance of zero over a year, but this is a balance on paper. Month by month, in reality, you have an unbalance. And so you need to use fossil fuel in certain months or to have a big interseasonal energy storage infrastructure. So the corrections are to do the energy balance on a shorter time, but the real physical solution is to strongly reduce the energy needs, so to lower the imbalance, to lower the amount of storage required. The other part of the project, and I go to the conclusion, is comfort assessment. We do measurements and interviews in a series of case studies to enrich the ASHRAE Global Comfort Database, and to highlight the role of air velocity in providing comfort in summer, as we can see in a number of case studies which are documented in the project, and how it is described now in the most recent standards. How air velocity can be formally also an element of thermal comfort in summer, to be designed together with other systems. Cross ventilation or ceiling fans can help to deliver that. I send you to the case studies to find information on all these things, because this is just a short introduction and appetizer. My only conclusion is, in buildings, probably we could think that adaptation is the same thing as mitigation. A good envelope with high external insulation, thermal mass, good shading can create buildings that are able to cope with extreme events better than normal buildings, and at the same time will reduce the energy needs for heating and cooling, so reduce the CO2 emissions. All reports and webinars are available at the website. I think it's time to give the floor to Professor Guilherme.
Okay. All right, guys. So we'll be showing you the results of ABC so far in two main areas. These are some weather files that we've produced. So we've created new files that reflect the expected changes in future climate, but also work that we did on weather indicators. So looking at how we are able to characterize weather and its challenges. Next. Okay, so the summary of my short talk today is I'll briefly talk to you and remind or even just see it again. What are the upcoming climate challenges that we expect to have as a planet? Then we'll look at our work on generating future weather files that can be used in thermal simulation. We'll just briefly show you the files that we've created that are freely available from the project website at the moment. We'll then move on to some other work that relates to ABC and weather impact on sustainable construction, and we'll show you the results of applying these files into the design of kindergarten, and we'll look at the impact that we expect for future weather in the performance of this design in the locations that are the main target of ABC at the moment. Next. Now, the challenges that we expect to have towards the mid and particularly the end of the century are still subject to a certain amount of uncertainty, in the sense that we may be able to overcome part of these problems and address them, and that's kind of an open question. And the question, looking at the figure here, is whether we'll be towards the red line, which is quite catastrophic, with an increase in temperature of up to 4 degrees, or are we going to be towards the gray and yellow line? In either case, we have a significant challenge for the African climate that is already quite warm. And of course, it's quite sad to know that for colder countries, this is kind of a very different impact. But for warmer climates, it is a very, very difficult challenge. Next. What's the current scenario of the use of fossil fuel? It's still the dominant source of energy, and because we have an increasing need for energy, in particular in developing countries that are increasing their standards and the overall productivity of the economy, and they are unable to do it relying solely on renewables at the moment. So we see a scenario where fossil fuels are already way beyond. So our use of fossil fuels has already exceeded what we should. And we see that the trends of bringing this down are not very clear for the next decade for many reasons. And for that, with this in mind, we can expect that our capabilities of addressing the climate change challenge is limited, at least in this decade. Next. The building sector around the world has a really, really important role to play. So if we think that up to 70% or more of climate change is driven by our use of fossil fuels, more towards 80%. And if buildings use about a third of these fossil fuels, it's clear that if we improve buildings, if we make buildings less reliant on conventional energy, then we are obviously contributing to addressing the problem. To have a building that relies less on conventional energy, we can, of course, reduce the building energy demand, so use more passive means, or concurrently, we can also use more renewable energies at the building level. In the case of ABC, we are more focused on reducing the building energy need through passive approaches. Using passive approaches in a warming climate, and in the climate in Africa that's already warm, is really, really a big challenge. Next. Now, where are we? So, as I said before, we already are seeing the effects of climate change. If we're not careful, we'll see super catastrophic, let's call it, effects. And as I said, these effects change throughout the globe. And so in the particular case of Africa, the effects are more severe. Next, Ron. And what's interesting is that as we see an increase in urbanization also in Africa, we have these problems densely concentrating in cities that can become pollution and heat islands. Next. There are a lot of existing studies of the impact of climate change in buildings. They look a lot at increased cooling demand and decreased heating demand, which is a result that we will always get if we simulate an existing building with warmer climate. In terms of using passive methods and strategies, we have less of these focus of the studies, so it's useful and relevant to see what can we do with this warmer climate by relying on passive strategies. Next. Now, when we think about weather files for energy simulation, we have a requirement of a large amount of variables shown here in the figure that allow us to then simulate the building internal temperature, comfort, energy demand, using, of course, 3D geometries, which we are all quite familiar with. In terms of, because these hourly yearly files, so these are files that have hourly weather for a given location for a year, and because they have these many variables, they become quite a challenge to update, because of course we need information on all these variables. We need expected changes to all these variables to update the files. Next, Sean. And how do we do that? So we take existing typical mean year files from one of the free, there are many free locations where we can find good quality current weather files for many locations around the world, including Africa. Of course, this doesn't mean all locations, just many. And in the case of ABC, we started off with the files for Africa and Europe, the selected 9 locations in Climate One building database. Next, which is free, quite important. So to go into a typical year, so take a typical weather file from the 2010s, let's say, and take it forward to 2050 and 2090, we need to know future changes in all of these quantities seen here, in these variables seen here on the screen. So as perhaps you're already familiar, in terms of future climate, we expect both an increase in average temperature, but also increase in the shape of the temperature throughout the day, and also an increase in the magnitude of extreme events. Go ahead, Sean. Now, to simulate and to obtain files for urban locations, which are relevant in the context that we have an increased movement towards urbanization. And so, since we don't have weather files current or even much less future for all locations, we can start concentrating on urban locations. And so for urban locations, we have new challenges when we want to have future climate files, and that relates to the grid, so the resolution of the global climate models that predict future climate, that are freely available databases of future climate that usually have a grid, a simulation grid, that is very large for representation of particular effects around a city, even for a big city. And so we need to go from the large-scale models to regional climate models, which are submodels with more detail that are fed by the global models. Now, the regional climate models for Europe and Africa have also different grid size, where Europe has a smaller grid size and then Africa has a bigger grid size. So as we go to this downscaling, where we're using the big models to push boundary conditions into these regional climate models, as we do that, we are faced with regional climate models that have more definition in Europe than Africa at the moment. Next, Sean. So in the case of Europe, our grid resolution is about 12 kilometers. In terms of Africa, the grid resolution is 25. The problem with the big grids is capturing the urban, the large city effects. As we know, the city affects the climate, and so, as you can see on the right side of this slide, the European model, because of its, I would say, reasonably sized grid, if we can say that, as you can see there, as we go to London and Paris, two very big cities, you are able to identify a warmer city center compared to the outskirts. So all the circles there in the image on the right are grid points of the model, and it's quite reassuring to see that the city center is up to 1 degree warmer than the outskirts, as one would expect, in light of urban heat island effects, which are completely well known and recognized and studied in these large cities. So the models for a 12-kilometer grid are quite reasonable at picking up urban heat island effects and even increased urban heat island effects that we may have with this future weather. For Africa, we're not there yet because the grid is not as good, but we can expect quick improvements in this field. So I wouldn't say it's a barrier because we're taking a first step here. And as we move along towards the latter part of this decade, we'll have improved models in both contexts, because of course computation power keeps getting better. Next row. Now, how do we take current weather files and turn them and move them to the future? So you probably know that current simulation files for a typical mean year, let's say, of Valencia in Spain, they use a typical month, the most common month of each of, in this case, 15 years. So you take 15 years of measured data, and then you, for each month, you try to find the month that is more typical, more representative. And then you compose a year out of 12 months that often are from different years, which is fine. And you then have to bridge a little bit on the last day of the month and the first day of the following, because you have some discontinuity, so you smooth it out. And this is an established method to have a representative year. Now, as we go into the future, we take the regional climate model data to understand the changes that we can expect in average years. And so what we do is we generate a new set of future months, and then we use the same methodology to assemble our TMY for future weather. Now, just to clarify something very important is how do we go from current to future? Because as you know, we have an increase in temperature. What happens to these data points in terms of air temperature, dry temperature? So they go up. And then in addition to going up, we also find that in future, there is an increase in extremes. So they are both increased in temperature, but often they are also stretched. So you have more extreme periods. This is an approach known as morphing that is able to, let's say, mimic a future file from current files. Now, what we are doing for the ABC files is we're using morphing with high quality databases from the international weather modeling efforts. So we are using high quality future predictions to understand what are the differences between current and future weather. And those are the drivers for the morphing that generates the future weather files. Next, Ron. At the moment, or in fact, within ABC, we developed all the files you see here. So the current file is not here because it's nothing to do with us. It's from the free existing database. And then you have these links in our website of the project where you can download the future file for 2050 and then 2090, okay? The current file, of course, comes directly from the existing database. And these are the locations. They are related to the composition of the ABC consortium. So they are not, let's say, fully representative of the challenge for Africa. They are not fully representative of Africa, but they are a depiction that relates to our consortium that, of course, has an explicit goal of being as broad as possible, and you can see it, but of course still limited because we are just a set of different groups and people working in this context. Next. When we try to characterize weather, and of course now we have new files, we can look at current weather characterization and future weather, and of course we can do it in different ways. We can see the impact of these files on simulations, and we'll see that in a few minutes. And we can also look at what's the impact of these files in terms of the current climate classifications. So see how they evolve. Let's say if a climate goes from being warm to being very warm, that's another way of looking at it. So no simulation there, we're just looking at the raw data and how we can classify it. That's a second way to do it. A third way is to see how many hours did we have in a given climate that were suitable for natural ventilation, and how these, let's say, hours of suitability or nice weather for natural ventilation, how they evolve in the future. So there's different ways of looking at it. So one very common indicator, or perhaps the most common, is heating and cooling degree days. That allows us to have a measure of the severity of the climate in terms of how many hours do we have above a certain threshold. And for cooling, that's known as a base temperature for cooling and a base temperature for heating. Common base temperatures for both of these are for heating 19 degrees. So we will then be counting the hours and also the distance, how much further down from 19 are we. And by adding all of these up, we obtain the heating degree hours in this case. And then for cooling is the same, but above 26. Next. As people have tried in the past to improve these concepts in order to understand how passive approaches for cooling in particular impacted the cooling degree hours, we can find different research efforts, which I'll just go in briefly. We have a very good discussion in some of our deliverables in ABC, which are on the website. The idea here is, let's say, if there is wind available, as Lorenzo already mentioned, if we consider the cooling effect of the wind, we can have a quantitative measurement of this effect by introducing different adjustment coefficients in the cooling degree days, and we can find them for wind velocity, we can find it for buoyancy effects in terms of being able to use buoyancy during the night to improve and provide night cooling to the building. You can see that on the bottom of the slide. And these are all, let's say, empirical adjustments to the existing expressions that allow us for some quantification of the effects. I would say the vulnerability of these methods is the more we try to incorporate these factors, the less the expression becomes clear. It becomes a little bit harder to understand. And also the rationale from a physics standpoint, we can see it's there. So we can see tendencies, more air velocity, more convective cooling, that's fine. But the actual rationale for the precision of these coefficients is very hard to convey because, of course, we are now in the realm of empirical correlations. Those are kind of okay, but they have these limitations. Next, João. And continuing on this, we find that the application of cooling and heating degree days in different research efforts and different locations give us a quite broad range of the reference temperatures, which also on the one side may be a manifestation of the need for local adaptation of these comfort standards, which is a known fact. But on the other side, it may be quite difficult and a bit confusing to follow. Next. In terms of indicators for the base temperature, we can find two main trends. So we can refer to as static. So when we say that the reference temperatures for heating and cooling are steady, and then the more typical numbers we find are for heating nearly 19, and then for cooling 26, and the other significant tendency in this area is to adopt and apply the adaptive comfort temperature approach to measuring thermal comfort. And by doing that, we then incorporate the average temperature, outdoor temperature in the last 30 days to these heating and cooling threshold temperatures, and we obtain the expressions shown on the bottom part of the slide. Next. Now, using the ASHRAE classification, which was shown in the previous slide, we can look here in the table, in the bottom part of the slide, we can look at the impact of expected changes in future climate to the different locations in current weather, the first line on the table on the bottom, mid-century and end-century. It's quite a good image to understand that we have an increase, let's say, level of yellow and orange as we go down, as expected, because the climate's getting more and more severe. And the best case we have for Africa is for the climate to become hot. And then on the other half of the locations, we have a prediction for extremely hot. What can passive approaches do in a climate that is becoming extremely hot? I think the main take home in that aspect is that winter and the mid-seasons become seasons where these passive approaches can make a very good contribution to the cooling of the building. So we can eliminate cooling in significant periods of the year, even in a warming climate. It just means that we are starting to rely on these passive cooling methods, sometimes even in what used to be winter, spring, early autumn. Now, as we move to the super warmer parts of the summer, that's up for discussion. For instance, Lorenzo and other researchers focus more on an idea that we should try to pass through these extreme periods, still trying to do the best with passive methods, which may be a very good approach, but is something we need to think and experiment with and see whether we can do it, or whether we will need active cooling, but only in very, very short periods of the year, which often coincide with very, very high sunshine availability and therefore a lot of renewable energy to power active cooling, which may be a positive aspect to consider. So this is something we definitely need a discussion that's already ongoing and will surely continue. Next. Now, as we look at these passive cooling indicators, we have, again, quite a broad set, going from indicators that consider variations in internal temperature throughout the day, so a bit more complex. They consider the need for the outdoor air to be at least 3 degrees colder than the indoor in order for it to contribute to the cooling. We also have indicators that consider the wind effects, but then, of course, we have to consider the reduction in wind availability in these urban contexts. So this is quite, I would say that any wind-driven cooling is very, very hard to simplify, because it becomes very much related not only to the urban context, street shape, and also building shape. So it's quite quite a challenge, and some of these climate cooling potential indicators that exist try to bring in all these factors, which is nice for us to get a better idea, but again, at the expense of becoming more and more mysterious. Next slide. This is another variation of these indicators. I'll go forward, otherwise we'll become short on time. Go ahead, João. Now, as we apply for instance, one of these natural ventilation availability indicators, we see that the number of weeks where we can expect to do daytime cooling by natural ventilation varies a lot throughout our climates, with the extremes being Lomé, where it's nearly 0, and then we see almost half of the year in the other locations. So with the exception of Saint-Denis, Dakar, and Lomé, in the other locations we have very high availability throughout the year. Next slide, João. But then as we move to 2050, we see a significant reduction, with the exception of Mid-Belt. In all the African locations, we have a very high reduction in the number of weeks where we can expect natural ventilation to work. And in 2090, next slide, the scenario becomes even worse. On the axis here, we went up by almost an order of magnitude. So we are now losing many months, let's say, of this potential. So these are pretty negative news in terms of what we can do, whereas now we can do a lot. In the future, it's going to become much more challenging. Next slide. If we simplify our analysis of the outside weather, so it's another way of looking at it, and we just characterize the current moment of the day by just saying whether it's too cold for natural ventilation, and existing research points that whenever outside is less than 10, people will become very reluctant to open the window. And then between 10 and 26, we have our, say, optimal range. And then above 26, depending on locations and local comfort and adaptation, we may be on a too warm case. So this, what you're seeing in this slide, I would say is the simplest way to characterize, because it's so simple. It lacks a lot of detail. So it's kind of a trade-off as usual. Next. If we apply this, we can see in green when it's good, in yellow it may be possible, and in red it's too warm, and then of course blue is too cold. We see that in terms of the Dakar, Saint-Denis, and Lomé, we already start off in a pretty negative standing, even at current weather. As we move to 2050, go ahead, Sean. We lose up to 10 weeks in these African locations that become too warm, and these are weeks that are displaced from weeks that were suitable. The yellow, now they become red, too warm. So it's just another way of looking at the same problem. Go ahead, Sean. Okay, in 2090, aggravation in general, and that of course extending also to European weather. Go ahead, Sean. Now, if we take, so that was one way of looking at these impacts in terms of indicators of climate. Another way is to take a design of a building and simulate with these files. And our approach in ABC was to take one existing building that we know that has good performance already, so it's already been used, has, of course, external shading, good external insulation, and natural ventilation capabilities, and see how it will behave in future weather, both in its location. This is a building in Lisbon. In fact, there's 20 of these, and in the climates that we've seen before. Just to feed the discussion, I hope we'll have time. I'll try to move fast. Just to feed the discussion with Lorenzo, I was at one of these last week, and it has babies inside and little kids. So it's a kindergarten, of course. And what they told me was last summer, when in Lisbon there were 40 degrees, they had the kids in just diapers inside because it was so warm. Because, of course, this building has no mechanical cooling, but it has, I would say, a very strong recipe of passive measures, meaning night cooling by natural ventilation, very high internal inertia, external insulation, external shading, and buoyancy and wind-driven ventilation. Go ahead, João. And in this slide, you can see a bit of it. So the air comes in either through the window or behind the radiator. This, of course, also needs to work in winter. So we preheat the air in winter, in summer, of course not. And then goes out through chimneys that whenever there's 2 stories, they go across even classrooms. So let's say if you have one classroom above the other, the chimney is inside the upper classroom and acoustically insulated. It's kind of an interesting approach and it works well. You can see the exposed concrete on the top right-hand side image there. Go ahead, João. Go, because we don't have so much time. Just a quick note, you can then either consult our report or existing publications. This is a building and a system that has been measured and also used to calibrate simulation models or to confirm that the existing simulation approaches are adequate to design and predict the behavior of these buildings. That's also a relevant question, of course. Can we rely on these models? Next. Go ahead. Let's not go here for now. In terms of characterizing the airflow through the chimney and behind the radiator, etc., we used a combination of detailed CFD and then bring the discharge coefficient calculated by CFD into the Energy Plus simulations. That's another area where there's still a lot of issues. A quick note to say that these buildings operate in the daytime in natural displacement ventilation. So they have a stratified temperature inside that Energy Plus is also able to characterize with a simple model that is implemented there. Go ahead, João. This is just airflow calibration. No, there's no point here. Next, João. The models of the buildings were implemented in Google SketchUp and then brought into Energy Plus. These are all freely available tools, which is important for this context. This is just a description of the passive strategies in the building. You can go back later if you are curious, go ahead. And then in the case of Lisbon, the simulations show that on a yearly analysis, the air quality meets the standards in 95% of the time. Only in 5% of the hours we are above the CO2 ideal thresholds. And in more than 90% of the working hours in terms of temperature. We'll look at other indicators just to say on the left side, you can see the predicted operative temperature. And we have about 10% of the hours above 26 operative. And this is a typical year. Of course, last year when we had several events of 40 degrees in Lisbon, that's when the babies were with just diapers. Next slide. If we run the adaptive comfort model, we are within 99% of the time within the acceptable temperatures for the range. Go ahead, João. The predicted energy consumption of the heat pump for heating and other aspects of the building is less than 90 kilowatt hour per square meter per year. And of course, we are way below the average for kindergarten, which is around 200. These are measured data. Ours is simulated data. Go ahead, João. And then as we bring in the effects of the climates and the different cities, we see that to meet the comfort range proposed by the European standard, we have, of course, significant mechanical cooling demands in the more difficult and, let's say, demanding African locations. And this demand is, let's say, linearly increasing towards this century. In the milder European climates, what we see is an exchange between less heating demand and more cooling demand, whereas in the toughest and warmest, in this case, climates such as Dakar, we see just an increase in cooling demand. Next slide, João. And of course, it's kind of linear, as you could expect. The more cooling degree hours we have, the more demand we're going to have. And the same happens with less correlation for heating, because on the left there, these are, of course, lower values. The stronger correlation is found on stronger demands for cooling. Next. Just a conversion into primary energy demand for all the climates, and just a second look at this expected process where we have increasing demand in this case, in this building towards the end of the century. Next, João. And that's it. Thank you. We can go into discussion, questions. Thank you.
Yes, thank you, Professor Guilherme. A lot of was covered. Thank you for that. I would check the chat, but I invite Professor Lorenzo to add something to the discussion and perhaps address some of the topics presented, especially regarding the thermal comfort. I think that's the main, the center of our discussion.
Yeah, I think the Guilherme has represented very well the challenges and the opportunities that we have with having more months where, for example, in Europe, definitely we will need to discuss how to achieve comfort in warm conditions, because the shoulder seasons are. So we had a very warm October, for example. So there will be a lot of need for having good envelopes to avoid using active systems in those months, so to extend the cooling season, and at the same time the worst weeks might be an increased challenge for passive techniques. One way to improve things might be that night, since the air at night is in some parts of the year becoming a sink which doesn't work anymore, probably there will be a need for passive techniques to look more in detail to other sinks, like the ground with ground exchangers, which is difficult to do in already built cities like European ones, but might be an ingredient in new urban situations that are being developed, like in Africa, where many new buildings and many new districts and cities will be built in the next decades. So this could be still included into the design to a certain extent. And there are these new possibilities of using the sky as a cold sink, which come from these cool materials and even super cool materials, which are part of our exploration in the project. These new materials, which are copied from nature, from the African ant and other animals who are able to communicate radiation through the transparent window of the atmosphere, so to concentrate their emission on particular wavelengths in which the atmosphere is particularly transparent, so that they can in fact have a net transfer to the sky even under the sun. So there are some of those materials where the temperature of those materials is lower than air temperature under the sun. These are being developed, are being transferred to mass production. In certain cases, we have to see how those develop and if they become actually available for our design. So there are a few new opportunities and definitely a big challenge that Guilherme has well illustrated. There might be some other discussions and possibilities which are connected with this adaptation, maybe the new ideas of personal environmental control equipment, where you are not able to passively cool the entire building, but you are able to locally provide some more comfort. So the issue of ceiling fans or desk fans or other types of localized comfort concepts. So there is a lot of work to do and probably possibilities, but definitely we have to be very realistic on the fact that the night cooling potential is being limited by the changes if they happen at the scale that let's say the worst case scenarios will obviously it's a catastrophe in many ways, and this would be a part of the catastrophe. So that would be my comment, and the fact that we are trying to see, and I invite everyone to see in the deliverables on materials. We might have a new chapter on cool materials, which will come. It's not yet ready. So maybe I would be very glad to have questions from the audience also, besides the comments that I can. Okay, there are some, probably a question from Regis.
Exactly, Regis Maya just sent us about the morphing weather files. If it's generic or depend to the sector, physical data to be simulated for the building design or agriculture, for instance. So that if I understood correctly, if these weather files can be only for building simulated or
also for climate applications. By please, Guilherme.
My comment, and of course, let's just be realistic. We are a group of mostly building scientists, and so we're not climate scientists. At least I'm not, and I think also Lorenzo is not. And the point being, so for Regis, what we're doing with our morphing and production of future files for energy simulation is making an effort to incorporate state-of-the-art climate research into building applications. So for that reason, we take our building files, the ones who characterize the weather, let's say, for the building simulation, and make the adapted files with the state-of-the-art data. This state-of-the-art data has then other applications by other groups into these different areas. And in that sense, our weather files are not meant to be a reference for other areas. They are meant to be used solely to characterize impact in buildings, but they are representative of outside weather. That's true. So you can look at it also from other angles, I would say.
And if I can add, there is also an effort to provide, let's say, more data on present weather, local weather, because obviously in Europe we have installed and we had money available, which is not unfortunately being available to colleagues in Africa. And this is another of the inequalities that we have to signal to the United Nations and to the action that we need to do. We need more research, more investment in research and universities in Africa. in general, but certainly inequality should be removed. And so we will install some weather stations to add data to present recordings of present weather. And there is an initiative to which we participate, which is installing weather stations around Africa. And again, you can find it in the deliverables, or if someone is interested, we can send information about that, which obviously those data will be basic data for use in various sectors.
Yes. Before we received another questions, before we move to the questions, I just wanted to ask Guilherme, because I see the difference in the mesh in the grid from Africa to Europe. So how can we equalize this difference between the meshes? I mean, is this more a policy approach, or the academia, how we can make it more even, the data available in these locations?
Again, with a certain being careful, because I'm not an expert, but my perspective, my guess, I wouldn't even say educated guess, just guess, is that we are looking at, unfortunately, just another reflection of the current asymmetry in availability of funds and research efforts that Lorenzo just mentioned. Unfortunately, I think you also see it in this resolution issue, but I think it's going to get much better as we move along for both locations, and it will become, towards the end of this decade, a non-issue. So in a way, I think we're in a good direction. But of course, you can see an asymmetry there, unfortunately.
Okay, yeah, unfortunately. We have two more questions from the chat. The first one is about, on slide 17, there's a table presenting the base temperature in many locations, where it is defined by comfort or balance. But so why isn't defined by the same way, basically?
Well, this what you see there in this slide is just a survey of existing base temperatures used in different studies. The justifications for these differences, I think we can only find if we go into more detail into each study. I think that we unfortunately suffer from excessive complication in this area, because you see all these different base temperatures, people coming up with coefficients for this and coefficients for that. And as we do a limited overlook that we did about this topic, I think I find it to be an area where there needs to be some tidying up and consolidation of ideas. And for us to bring in complicated approaches, they should be very, very well justified. And in some cases, that doesn't happen.
Okay. There is another question. What should be stated in the document, anticipated 2.5 or 3 degrees Celsius, in order to raise attention, or should we use 1.5 reference? So basically, if I understood correctly, is about the
what is the
temperature
future,
increase?
Right?
Yes,
is the question.
How optimistic or pessimistic should we be, basically?
I think, again, it's just a personal opinion. I don't think that we will be able to be within the best scenarios in terms of future climate, but we will also be able to avoid the more catastrophic expected futures. And so the area around 2 degrees may be the current, let's say, more consensus expected outcomes towards the end of the century. So 2 degrees, just to clarify, if I had to say something about it, it would be that.
probably that's why we need to start designing buildings that are lower in energy needs and demand, and use as much as possible passive and cross ventilation for cooling and other strategies for heating, especially in Europe.
Also, because this is again doing both things, is doing adaptation and is part of mitigation. Using less energy in buildings is, as Guilherme has obviously presented at the beginning, is an important part of the strategy, and the new United Nations initiative driven by this global alliance for building and construction is exactly to bring into the negotiations and more than the negotiation, in fact, hopefully, the fact that buildings are part of the solution of the climate crisis, and so we have to think of adaptation to the change and a big steps towards reduction of the problem. I again, not an educated guess, I guess. If I look at current disasters in every part of the world, and now starting also to occur in the north, which has been to some extent protected till now, I hope we can steer more quickly. I see examples of where this can be done extremely quickly, which is, for example, mobility. It's not the buildings, but it's something which can be done together with the buildings. And we have cities which have created a network of cycling paths, of streets protected around the schools where cars cannot access. And so the way we move from using cars weighing 2.5 tons each to using very light vehicles, this can be done very fast if we become aware of the dangers we have. So I would say technically and politically it's still feasible if the rings are heard.
Yes. One last question.
That's again,
thank you.
guesses and
yes.
discussions, which anyway come also from analysis in another research project we have, Fulfill, but not the time to bring that in now.
Yes, there is one last question from the chat, which is about the blue and green infrastructure and how the morphing of the weather files could take these changes into account, since they are also impacting the urban climate.
It's a good point to make, because of course, as we look at future is not only the weather, or the future weather changes in urban context are highly dependent not only in the pathways of emissions, but also in the pathways of cities, in the sense, are they going to be more green? Are they going to have, again, new mobility solutions, which I think we will see that, which is wonderful. And so addressing that question, the answer is, currently we have predictions that have these different scenarios, both for urbanization and for emission pathways. The way that building science will incorporate future weather predictions to make the future weather files, and of course we should be updating these every time we have updated weather predictions and pathways. The way we incorporate that is because the pathways, so the future conditions that are used to predict future climate, that then feeds into our weather files. So the pathways will be updated to include, let's say, greener cities, less pollution in cities, less global emissions. As these pathways are updated, we bring the results from the regional climate models into our morphed files. And so we are on a second level of feedback from the studies of future climate, that they themselves incorporate these better pathways. So the answer is, those things are considered already now, and as they become better, they will also be considered as we update the files. We, and of course other researchers, most likely others. I'm sorry, this is a bit complex to explain. Maybe I was not very successful in my explanation.
No, it was
Well,
a good
It
explanation.
it could be that our Anwar asking this question there might be also a possibility that we include those infrastructures in those in the tools for design. Besides, I don't know, ground exchange, there might be
So green surroundings, let's say.
green
right?
surroundings and so on.
Yes, absolutely,
Yes.
absolutely.
But obviously, this again at large scale that might then be included into the general models also.
Mm-hmm. Mm-hmm.
Yes, it was a good overview. Complicated question, but good overview.
But the question is on how this influenced the
Yes.
morphing. So that
Yes.
the response of Guilherme was directed to that. Absolutely.
Mm-hmm.
We have reached our limit, but I just want to show you real quickly where you can find the weather files that Guilherme presented today. So this is the project website. And if you go here up, there is a weather files section. And if you click it, you have an overview of the locations, also a short explanation. You can access directly and download the reports where you have the technical explanation about the weather files. And here you can download them for the 9 cities that we selected in the project. So they are open and freely to be downloaded and used, and hopefully to be tools for better buildings, for simulating and designing buildings with that consume less energy with less energy demands. And so that would be a closure for the webinar today. I would like to thank Professor Guilherme and Lorenzo for the great explanation and discussion. This session was recorded. It will be available very short on our website as well. And I invite you all to keep in contact, to visit our website, to follow us on Twitter, on LinkedIn, because we have many events coming up about bioclimatic, about policies, related topics to the one that we discussed today. And I would like to thank everyone for joining us and the questions and contributing. It was a pleasure. Thank you, everyone, and